Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
As we have studied in dynamics of fluid flow, that are various types of flow, that is Euler's equation of motion, Navier Stoke equation of motion, as well as Newton's introduction. As we have studied in dynamics, different types of fluid motion, that is Navier Stoke equation, Euler's equation. Now we have derived what is Euler's equation, in which we take pressure as well as gravitational force into consideration. Now we will derive what is Navier Stoke equation, in which we have to consider the effect of pressure force, gravitational force, which will be somewhat called as a body force, and the third will be a viscous force. So we have to take into consideration three types of forces. Navier Stoke equation. Now let us study what is Navier Stoke equation. In Navier Stoke equation, we take effect of pressure force plus gravitational force plus viscous force is equals to mass into acceleration. So this is the force which we consider, that will be addition to viscous force. Now over here we'll take this gravitational force will be termed as a body force. This will be termed as a body force, and pressure force and viscous force we have to take into consideration. That means pressure and viscous force, when we take into consideration, we have to consider for pressure sigma, that is a longitudinal stress on the fluid element, and for viscous force you have to take tau, which is actually called as the shear stress on the element. So sigma, tau and body force will constitute your equation of motion, that is Navier Stoke equation. Now let us get into a detail. Let us consider small control volume. We will consider a small control volume having a volume of dx, dy, dz, and let us consider this volume, and this will be in a Cartesian coordinate system. So we will consider this into a Cartesian coordinate system. So let us draw this part. We will take this as okay. So this is a fluid element which is having a length of dx along x direction, length of dy along y direction, and length dz along z direction. So this part over here is dx, this let us consider dz, this as dy, and considering this as x-axis, y-axis, z-axis. Let the planes be denoted by A, B, C, D, E, F, G and H. So we have drawn the control volume, whose volume will be equals to dx, dy and dz. Now next part which we need to know over here is a small definition of tensor quantities. Now tau over here is a tensor quantity, and this depends upon two variables, that is it has 2 degrees of freedom. So it will consist of two subscript 1 and subscript 2. Now what is subscript 1? Subscript 1 will denote the plane in which this is acting, for the stress is acting, and 2 will denote the direction in the plane. So since it is a tensor quantity, not only it requires a magnitude direction as well as it requires the plane in which it is acting. So now we'll see what are planes over here. Now this is our x-axis, this is y-axis, this is z-axis. Now the x-plane, which is this plane, that is plane A D G E, this is x plane. The distance between two x plane is given as dx. The distance between two y plane is given as dy, and the distance between two z plane is given as dz. So over here the x plane will be this entire plane. So the distance between them is dx. The y plane is this plane, the distance between them is dy, and the z plane, the distance between them is dz. So these are the three kinds of plane. Now on these three types of plane we are going to have a force which will be acting. So if the plane is x plane, so this will be an x plane, and we can apply in two directions, rather three directions. We can apply the force in all three directions on that plane, that is x, y and z. So if this is an x plane, so in this direction along x direction, this force will be tau xx, x plane x direction force. Next will be the force along y direction, so this is tau of x plane y direction, and the third force will be tau of x plane z direction. So this is along z direction, this is along y direction, and this is along x direction. But since this x tau xx is normal to this area or perpendicular to this area, the effect of this kind of stress is not a shear stress, this will be a longitudinal stress. So hence whenever we have a stress which is normal to the area of cross section, will always denote by sigma, and in that direction, or we can also write that as tau xx, but for our convenience we'll write that as sigma x. So we have seen all the three types of plane, and we have seen all the three types of stresses which will be acting on that entire part. Now what we need to do is we have to apply in each and every plane all the types of stresses. So we have drawn all the planes. Now let us draw all the stresses in this control volume. So now we have this control volume over here. Now let us draw the stresses. Now the first stress which we are going to draw, that will be along x direction. So the first stress we'll draw, that will be along x direction. So this will be sigma x, this is also sigma x. But now let us see this properly. So this is x-axis, this will be y-axis, this will be z-axis. So this plane will be x plane x direction. Now this is changing by a distance of dx. So over here this is sigma x at the origin, so this will be sigma x plus dx. Now next part, we'll see the x direction force in y plane. So this two are y plane, so over there we'll see x direction force. So the first x direction force should be in this direction, so tau of y plane x direction. So this will be tau of y plane x direction plus dy. Why dy? Because the distance between both the planes is dy. And the third will be along z plane. So let us consider this along this plane, these two planes. This force will be tau of z plane x direction, and on this plane, so I'll draw it over here, this will be over here, that is tau x plane z direction plus dz. So these are all three types of forces along, these are all six types of forces along x direction. Now over here we can split this into individual planes, so which I have drawn it over here. Now these are the three individual planes. Over here the force along x direction will be sigma x, along x plane sigma x plus dx. Along y direction, this is tau of y plane x direction, this will be tau of y plane x plus, this will, the distance between these two planes is a dy. And the third part will be along z direction. So if I consider this as point, so this is going towards left, so this is tau of z plane x direction, and the distance between two planes we have increased and we have split that into individual parts, so this will be tau of z plane x direction plus a dz. So we have seen all the forces which is along x direction. Now let us see all the forces which is along y direction. So over here this is our initial plane. Now we'll see all the forces along y direction. First we'll see in y plane y direction. So this is y plane, this is also y plane, separated by a distance of dy. So over here this will go down, this will be sigma y, this will be sigma y plus dy, because the distance between the two planes is dy. Now next plane will go along x plane y direction. So this is x plane y direction, so this will be tau x plane y direction, and at a distance it will go above, so this part will be given as tau of x plane y direction plus the distance between them is dx. So the distance between them is dx. And the last part which we'll consider over here, that is the plane which is behind, that is z plane. So this is tau of z plane y direction, and over here this will be tau of z plane y direction plus a dy, plus a dz, not dy, because the distance between these two planes is dz. So we have denoted all the y direction stresses. Now we have to denote on this individual planes. So let us denote on these individual planes. So the first plane which we'll consider is y plane. So over here this will be sigma y. So here this will be sigma y plus dy, because the distance between these two planes is dy. I have just split into distances so that it is visible to us. Next part we'll see along x direction. So this will go down, this is sigma of y, not sigma, rather this is tau of x plane y direction, which is going down, and over here this is tau of x plane y direction plus dx, because the distance between these two is dx. Next part we'll see along this z plane. So this is tau of z plane y direction, and this will be tau of z plane y direction plus the distance between them is dz. So we have represented x direction stresses, y direction stresses. The last we have to denote are z direction stresses. So let us see the z direction stresses. So the first stress which will denote over here, that will be z plane z direction. So let us consider this as the first plane of z plane. So this part which will go behind, this will be sigma z, and for this plane which we have drawn it over here, this is sigma of z plus dz, because the distance between these two is dz. So we have seen that part. Now let us see the next part for x plane z direction. So this is x plane z direction, so tau of x plane z direction at the origin, and over here this part tau of x plane z direction plus dx. So this is dx. Now the distance between is dx, and the last part which will be over this part, that is y plane. In y plane, this is tau of y plane z direction, and this will be over here tau of y plane z direction plus a dy. So we have seen all the three types of stresses on all the three types of plane. You can see the diagram is a bit shabby, but we'll denote on the individual planes. So when we denote on these individual planes, let us see this again. So first plane will be this plane, that is along z directions. So over here this will be sigma z. Over to this plane, which is at a distance of dz, so this will be sigma z plus dz. Next part will denote along x plane. So these are two x plane, so this will be tau of x plane z direction, and this will be tau of x plane z direction plus dx. Similarly, along y direction will denote this. So this force over here, this is tau of y plane z direction, and this force which will be tau of y plane z direction plus dy, since the distance between is dy. So we have represented each and every stress along each and every plane, both on the control volume which we have seen, which we have seen over here, and on the individual planes which we have seen it over here. Now what we have to do it, we have to apply Navier's Stoke equation. Now this Navier's Stoke equation will consist of three forces, that is force due to pressure, force due to gravity, and force due to viscosity. So the force due to gravity, which we'll consider as body force per unit volume. Over here, the force due to pressure will consist of sigma x plus dx, and all the sigma terms, because they are perpendicular to that planes. Sigma Fv, that is viscous force, that is the force due to tau, that is shear stress. So over here that will be parallel to those areas. So these all force which are parallel to the areas that we have to take into consideration, and that will be equals to what? Mass into acceleration along that individual direction. So now over here, let us see what is the net force along x direction from these planes. So the net force along x direction over here, what we'll do is we'll apply over here, that is Taylor series. So we know that sigma x plus dx will be equals to sigma x plus dou by dou x of sigma x into dx. So we know this. So similarly, for tau of y plane x direction plus dy, y plane x direction plus dy will be also given as tau of yx plus dou by dou y into tau of y plane x direction into dy. So these three things which we know by Taylor series. And similarly, tau of z plane x direction plus this will be dz will be given as tau of z plane x direction plus dou by dou z of tau zx into dz. So these are all these three things which will be applying in all Taylor series, will be applied in all higher order terms we neglect, and we'll write down over here summation of all the forces along x direction. So let us write this down. So let us write down all the forces along x direction. Now before writing down the forces, we know that the relationship between force and stress, that is sigma up is equals to force upon area. So over here we have to multiply by the area of cross section whenever we have to calculate the force. So now let us calculate this part. So now over here sigma x, this is sigma x and sigma x plus dx. The area of cross section over here is dy and dz. Similarly over here dy into dz. This is going towards left, hence negative. This is going towards right, hence it will be positive. So the difference between them can be written as over here minus of sigma x into dy dz into positive of sigma x dy dz plus dou by dou x of sigma x dx dy dz. Now this is the equation. Now this is the expansion of Taylor series and we have multiplied the area with it. So over here these two terms will go away. These two terms will go away and we will be only left with this term. Similarly over here the next term will be minus of tau. Now this is minus of tau. We'll first write down all the negative terms. So this will be along x direction denoted in red color. So this is tau of y plane x direction, which is towards left, and this is tau of y plane x direction dy, and that can be expanded with help of Taylor series. So this can be written as, along with this we have the other forces also, tau of zx which is going towards left, and this is tau of xz which is going towards right. So let us write down, this is minus of tau of y plane x direction dx into dz. This is what will be the area of cross section. Let us look into this. This is a dz and this is dx. That will be the area of cross section, plus of tau of yx into dx dz plus dou by dou y of tau of y plane x direction into dy dx into dz. So we have written this part, that is the second part for y direction, y plane rather, x direction. These two terms will go away. We will be left with only one term. And lastly we'll write down along z direction. So along z direction this is going towards left over here. Along z direction this is doing toward along x direction z plane, this is going towards left, this is going towards right. So let us quickly write down this. This is minus of tau z plane x direction into dy into dx plus tau of z plane x direction into dy into dx plus dou by dou z tau of z plane x direction into dz dy into dx. So we have written all the three terms, and what will cancel out over here will be these two terms. These two forces are equal in magnitude, opposite in direction. Hence whatever things which we have over here along x direction, that will constitute of two forces. This is the force due to pressure since it is perpendicular to the area of cross section, and this is the force due to viscosity, that is the shear stresses which is acting along x direction. So let us write this down. So this will be dou by dou x of sigma x into volume plus dou by dou y into tau of yx into volume plus we'll have dou by dou z into tau of zx into volume. So these forces, these two forces are shear forces, and these are what, longitudinal force, but that will be taken in terms of a stress force, in terms of pressure force. Similar to this we can write this over here, this as dou by dou x. This will be dou by dou x of tau of x plane y direction into volume, similarly plus dou by dou y of sigma y into volume plus dou by dou z of tau of Now let us analyze this. This will be z plane y direction into volume. So this we have written for y direction. And lastly, let us write down for z direction. So this is dou by dou x of tau of, this is opposite to that, x plane z direction into volume plus dou by dou y of tau of y plane z direction plus dou by dou z of sigma z. So on evaluation of all these three, we have got this equation. Now over here we can see the diagonal element sigma x, sigma y, sigma z, tau xy, tau z, tau xy, tau yx, tau xz, tau zx, and tau xz as well as tau zy. So all these three terms which we have considered. Now this will form a matrix called as a stress matrix. So let us denote this term. Volume can be taken apart, can taken aside, and over here we'll see a matrix. Its diagonal element is a sigma x, sigma y, sigma z. Then over here we have tau of y plane x direction. Here you have tau of x plane y direction. Next part will be over here tau of z plane x direction, tau of x plane z direction, and the last part which we will have over here, that is tau of z plane y direction and tau of y plane z direction. So these all 9 terms are forms a stress matrix. Now this stress matrix, we are not considering the rotational equilibrium. There is no, it is in rather a rotational equilibrium. That means the fluid is irrotational. Now irrotational means it is not rotating. Then these two quantities as well as these two quantities will be same. So tau of yx is equals to tau of xy, tau of xz will be equals to tau of zx, and tau of yz is equals to tau of zy. Now let us understand this part, how we have got over here. Now imagine this as entire cube. We have an entire cube over here. So this is the cube. Now over here you can denote all the forces. So this will be these two forces, similarly few forces. Now rotational equilibrium means what? It won't rotate clockwise, anti-clockwise, neither on any axis, that is x-axis, y-axis or z-axis. Hence these two stresses will be same. So we have seen that tau yx is equals to xy. Since it is in rotational equilibrium, that means the fluid is not rotating along any axis, that is x-axis, y-axis and along z-axis. So now next part which we are going to see is we are going to see body forces. Now let us see what is a body forces. Now we will define three forces. Let us define body force as B. It is kind of a force. Bx will be denoted as body force per unit mass along x direction. So we'll denote this part. Then similar to this, by dot will be body force per unit mass along y direction, and b dot z will be body force per unit mass along z direction. This is along z direction. So body force along x direction, y direction and z direction. Now what are body forces? Body forces generally consist of three forces. First, the gravitational force which is acting along a y direction. Then next body force will be electrostatic force, and then the last kind of force will be magnetic force. Electrostatic force, magnetic force, or the nuclear force, which are between the atoms. All these forces are called as what? Body forces, which is also acting on the body. But considering this body force in fluid mechanics is actually not calculating this body forces is not a part of fluid mechanics, so we'll just write this body forces in the equation, but we'll not solve this body forces as a function of x, y and z direction, or rather will not solve this in the equation. We'll just write down these forces. So now for Navier Stoke equation, we actually know that is F force due to pressure plus F due to gravity, or this is now called as body force, plus F due to force this will be force due to viscosity, will be equals to mass into acceleration along any direction. So now we'll just write down about x direction. Though for x direction, the pressure force will be dou by dou x of sigma x into volume, because pressure is acting perpendicular to the area of cross section, similar to stress which we have, that is longitudinal stress. Plus we will have body force per unit mass, or body force per unit mass we have denoted by that bx. Plus we'll have viscous force along x direction, so this is dou by dou y of tau of this will be y plane x direction into volume, and along with that we have dou by dou z of tau of z plane x direction into volume, which will be equals to, we have over here mass into acceleration, so let us write down this as equals to density into volume, which is equals to the mass, into acceleration along x direction. So this is du by dt, capital D, not small over here, du by dt, which we know this part as equals to, this part is equals to du by dt is equals to dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. So this is the expansion of the acceleration term. So now what we are going to do is we are going to divide this entire term by mass over here. So if you divide this by mass over here, this will be upon density, this will be upon density. So we'll get this in terms of, this is already body force per unit mass. If you divide this not by mass, we'll divide this by volume. So over here volume will go away, here we'll be divided that by volume. So over here we'll not expand this part, we'll just keep it as it is. So the ultimately what equation we get over here, that is dou by dou x of sigma x, plus you will get this as a bx per unit volume, which we already have, plus dou by dou y of tau of y plane x direction plus dou by dou z into tau of z plane x direction, which is equals to rho into du by dt, and upon here we will have volume. So this is body force per unit mass into volume divided by volume. So this can be taken as 1 upon rho, and rho will come over here. So just for the sake we'll keep it as it is, because we don't have to take this into consideration. We have to take all these three forces into consideration. So let us write down all this force in all the three individual directions. So what do we get over here? What do we get over here? This is sigma x dou by dou x plus body force per unit mass per unit volume plus dou by dou y of tau of y plane x direction plus dou by dou z of tau of z plane x direction will be equals to, now this will be density into du by capital dt. Similarly, we'll write down along y direction. So this will be dou by dou x tau of y plane, not y plane, this will be x plane y direction plus we'll write down the body force. So this is body force per unit mass along y direction divided by the volume plus dou by dou y of sigma y plus this will be dou by dou z of tau of z plane y direction is equals to rho into dv by dt, capital dt. And lastly we have dou by dou x of tau plane z, this will be x plane rather y direction, x plane z direction plus body force per unit volume, body force per unit mass per unit volume, this will be divided by v plus dou by dou y of tau of y plane z direction plus dou by dou z of sigma z is equals to rho into dw by dt. So we have over here this differential equation which consists of all the 9 terms. We know that these non-diagonal elements over here, these 3 non-diagonal elements are equals to each other. Now to solve this differential equation we will get 6 terms, because over here in stress matrix diagonally 3 terms we have and these terms are same. So, and body force per unit volume is just we are writing, but evaluation of this part we do not do because that is beyond a scope of fluid mechanics, not the scope of the syllabus. But over here we'll get the, after solving this part, what do we get over here? We'll get sigma, which is stress matrix, sigma x, sigma y, sigma z, tau of xy, tau of y z and tau of zx. These 6 terms which we have, this will be a function of its corresponding strain rates. Now why it will be strain rates? Because over here we'll have over here ex dot, ey dot, ez dot, e of xy, e of yz and e of zx. Now why we'll have stress and strain rate? This will be a relation between stress and strain rates. Now this will be a relation between stress and strain rates because we know by Newton's law that is stress is directly proportional to strain rates. Now we have seen this as the stress matrix or stress, which will be a function of strains. Now to solve this entire complex equation which we have seen over here, we'll need a few assumptions. Okay, the one of the assumptions over here is that first assumption we can see over here, assumptions for solving Navier Stoke equation. So So first assumption which we need over here, it should be that it should follow Newtonian fluid. Now what is a Newtonian fluid? That is the stress relationship, stress relation with strain rate. Strain rate should be linear, should be linear. That means tau should be equals to mu into du by dy raised to n should be equals to 1. The relationship should be linear and the fluid should be a Newtonian fluid. And next it should obey Stokes law. It should obey Stokesian law, or it should be a Stokesian fluid also. Stokesian fluid also. What is an Stokesian fluid? That is beyond the scope of our syllabus. So over here, these are the assumptions which we need to solve this entire differential equation. And the solution of this equation will be given, is directly taken into assumption. After solving this, we'll get the solution of this equation. The solution of this equation, how we have got, is beyond the scope of our syllabus, but we have to consider the solution. That is sigma x will give us minus of p plus 2 into mu dou u by dou x minus 2/3 of a mu into dou u by dou x plus dou v by dou y plus dou w by dou z. So we get sigma x as this term. Similarly, sigma y will be equals to minus p, that is pressure, into 2 times mu dou v by dou y plus not plus over here, this is minus of 2/3 of mu into this entire term. This can be written as del dot v cap. So that is continuity equation. Similarly, sigma z can be written as minus p plus 2 into mu dou w by dou z minus of 2/3 of, will get this entire term, that is del dot v again. So this is solution for sigma x, sigma y and sigma z, and the solution for tau x y will be given by simply Newton's law of viscosity, that is mu into dou u by dou y plus this is dou v by dou x. Similarly, tau of y z will be equals to mu into dou w by dou y plus dou v by dou z, and the last part, tau of zx is equals to mu into dou w by dou x plus dou u by dou z. So these are the solution of these 3 equations which we have got, that is sigma x, sigma y, sigma z, tau xy, tau yz and tau zx. So by solving the differential equation, now we have the solution of this is not in our scope of syllabus, but we have to use this equation and we have to substitute in the individual terms. So now we have got the value of sigma x. Let us just quickly write down the value of sigma x, that is minus p plus 2 mu into dou u by dou x minus of 2/3 of mu into dou u by dou x plus dou v by dou y plus dou w by dou z. Along with that, we'll write down the initial differential equation which we have written over there. So the initial differential equation which we have written, that is dou by dou x of sigma x plus body force along x direction upon volume, body force along x direction per unit mass per unit volume, plus we have got this as dou by dou y of tau of y plane x direction plus dou by dou z of tau of z plane x direction is equals to, that is rho into capital U, capital D by capital du by capital dt. So this we have got initially. We have to substitute the values. For that we need the value of tau xy. So tau xy or tau y x, so that was equals to mu into dou u by dou y plus dou v by dou x. So this is this should be derivated x direction velocity with y direction velocity with x direction, and we know that tau of zx is equals to mu into dou w by dou x plus dou u by dou z. So these are the values which we know. We have to substitute individual values in this equation. So when we'll substitute this, so let us substitute. We won't consider the body force term, we'll write it down later, and we will substitute this individual values. So now what do we get? This is dou by dou x of this entire bracket, so we'll just write down that entire bracket. So this is minus p plus 2 mu dou u by dou x plus, minus of, rather 2/3 of mu dou u by dou x plus dou v by dou y plus dou w by dou z. So this entire part we have got. Along with this, we'll neglect this term for time being, and then we'll substitute this term. So this is dou by dou y of tau of yx. So this is mu into dou u by dou y plus dou v by dou x. So these terms will have, and lastly dou by dou z of tau zx. So that is equals to mu into dou w by dou x plus dou u by dou z, which is equals to the right hand side of the equation. So now let us differentiate this part with respect to x, this part with respect to y, and this part with respect to z. Note that along with that, over here this term will always be there, and that is equals to the right hand side, but over here we'll write down this is the left hand side of the equation. This is the left hand side of the equation. Now let us differentiate this part. So what do we get over here? The left hand side of the equation, that is equals to, let us differentiate this inside. So body force per unit volume will write down later. So this is differentiated inside, so that will give us minus of dou p by dou x plus 2 mu into d square u by dx square minus 2 by 3 into mu, and this will be differentiated inside. So this is dou square u by dou x square plus dou square v by dou x dou y plus dou square w upon dou x dou z. So let us check this out again. Over here this we are differentiating inside, so that is minus dou p by dou x. So we have written it over here. Next term, so we'll check this out again. So we have differentiated minus, this is first term is minus dou p by dou x. So we have seen over here minus dou p by dou x. Second term will be, when this goes inside, this will be dou square u by dou x square into 2 mu. So this is dou square x upon dou square u by dou x square into 2 mu, and then this part will be derivated inside. So this term will be dou square u upon dou x square, that will be the first term. This will dou square v into dou x dou y, and dou square w dou x dou z. So this will be the term over here, so which we have seen, and 2/3 of mu will be as it is. Now the second term which we have to differentiate with, that is with respect to y. So we'll check this out. So this will go inside. So this will be mu into dou square u by dou y square, and this will be dou square v dou y dou x. So let us write down this part. So this will be plus mu will be outside, so this is dou square u upon dou y square plus dou square v upon dou y dou x. That is the next term, and after that what we have over here is the last term, in which dou by dou z is multiplied inside to both the parts over here. So let us write that down. So this will be plus of mu into dou square w upon dou z dou x plus dou square u upon dou z square. So this is the value of this entire part. So now over here we have to simplify these all terms. So now let us simplify these terms. So over here we will club the terms having second order differential equation, that is of second order. So this is of second order with respect to x, this is second order with respect to y, this is second order with respect to z. So let us club that together. So this is minus dou p by dou x plus second order term. So this consists of one second order term with respect to x. So this will be mu, which will be common. So this is dou square u upon dou x square plus dou square u upon dou y square plus dou square u upon dou z square. So we have seen this two term. This we can split into two parts. So first part will be mu into dou square u by dou x square. This second part will be mu into dou square u upon dou x square. So one of this part we have considered over here. Let us go over to the next part over here. Now this is the next part, minus 2/3 of this. So what we'll get over here, this will be 1/3 of this entire part. So this will plus, this is 1 upon 3 into mu. What do we get? That is dou square u upon dou x square. This is 1 minus 2 upon 3 mu. So we'll get this part. Similarly over here this mu will be going inside. This is the whole term, and this term, the difference between them, both of them, will be again 1 upon 3. So we can write over here plus 1 upon 3, that is dou square v upon dou x dou y. And then the last term over here, this is minus 2 by 3 mu into this term, and this is just this term over here. So this term can be written as plus dou square w upon dou x dou z, or dou z dou x, it doesn't matter. So we have got all these three terms. So now let us further evaluate this part. So we have got this equation. Now let us just simplify this all over again. So this left hand side becomes over here minus dou p by dou x plus mu into dou square u upon dou x square plus dou square u upon dou y square plus dou square u upon dou z square, and plus 1 upon 3 mu. Will take dou by dou x as common, so we'll get this as dou u by dou x, dou v by dou y plus dou w by dou z. So this is what is the left hand side. We have just taken dou by dou x common over here, and we have got this entire equation. So now let us write down this right hand side. So the right hand side, this entire part, which is equals to rho into du by capital dt, plus over here we'll have body force per unit mass per unit volume So this is body force per unit volume, which we have body force per unit mass per unit volume, which we have represented. So now if the flow is continuous, that means it follows continuity equation. It satisfies continuity equation, then dou u by dou x plus dou v by dou y plus dou w by dou z will be equals to 0. This means this term will tend to 0. So now when this term tends to 0, what do we get? The entire equation. Let us write this down. So that will be minus of dou p by dou x plus mu into that is dou square u upon dou x square plus dou square u upon dou y square plus dou square u upon dou z square. Only these terms will remain plus the body force. See over here, this part will be 0. The body force, that is equals to du upon dt. So plus the body force per unit volume, per unit mass per unit volume will be equals to over here rho into du by dt. Now this we have seen the solution of Navier Stoke equation along x direction. Let us see along y direction. So this will be equals to minus dou p by dou y plus mu. This term can be written as, okay, this can be written as del square times dot product of u. So this can be multiplied. This is del square operator. Now del square operator is dou square by dou square upon dou x square. Oh. Del square operator is dou square upon dou x square, dou square upon dou y square plus dou square upon dou z square. Now this is multiplied with a variable along y direction, so hence we won't have v over here. We will have we won't have u. We will have over here v plus body force along y direction per unit mass per unit volume. This is rho into dv by dt. And at the last part we can write along z direction, so that is minus of dou p by dou z plus mu into del square into w. So again del square is dou by dou x into dou square upon dou x square I cap, j cap and k cap I have not written, so that will also will be there along this part, plus body force per unit mass along z direction per unit volume into rho into dw by dt. Even here this is capital D. We can expand this part and then we can write the equation. Now this 3 is the solution of Navier Stoke equation, and this forms the basic form of Navier Stoke equation. I hope you have understood how to derive Navier Stoke equation. In the further videos, what we are going to do is we are going to simplify this Navier Stoke equation according to our necessity and according to our conditions. Thank you.